Okay. Yeah, so the one thing I forgot to write at the end of this example is just that the variable assignments actually satisfy the clauses that we were given, right? So this tour that we just computed, which goes, it starts here, goes down. Like that. It traversed x1 in the true direction. Oops. X1 was true. X2 was traversed in the false direction. And X3 was traversed in the true direction. And if we look back at our clauses, setting X1 to true satisfies Z1, right? And setting X2 to false satisfies Z2, as does setting, oh yeah, sorry. Actually, setting X3 to true doesn't help with the second clause, but we've got a positive literal in each clause, right? A true in each clause. Now, the last thing with this reduction was that we did a reduction to directed Hamiltonian cycle. Right? The graph we created here uses directed edges. We can actually convert that to our standard undirected Hamiltonian cycle fairly easily. And the trick is that I want to kind of represent a directed graph as an undirected graph for the purposes of this Hamiltonian cycle thing. And so what I do is I replace each vertex with 3. And it looks like, so rather than having the vertex V, I replace it with V in, undirected edge to V, and then V out. And all the edges entering V now enter V in, and all the edges exiting V exit V out. And to show you, let me just kind of sketch why this works, why this, for this particular thing, is like, let's say we had a graph that looked like this, right? A, and then it goes to B, and then there's another edge like this. So we want to make sure that if we just change it to undirected edges, you can't all of a sudden go ABC, right? Because that doesn't obey the arrow directions. So if we do this idea of replacing each vertex with 3, what we'll get is, we'll get A in, A out, B in, B out, C in, C out. Sorry, just writing all these out. Okay, I know it's a lot, all undirected edges for our 3 vertices. And now we connect them up, right? So there's an edge from A to B that will go from A out to B in, right? An undirected edge here. And then there's also an edge from C to B. So it's going to go from C out to B in, right? Like this edge. And that's it, right? And so you can see that the path that isn't allowed in the directed graph, which is ABC, in this new graph, it'll go A in, A out, B in, C out, C in. And it'll skip 2 vertices, B and B out. And so it won't be valid. Do you know what I mean? Like when you're trying to compute a Hamiltonian cycle in this, you'll end up skipping B and B out in our undirected graph. And so that won't be a valid Hamiltonian cycle. So you won't be able to violate these edge directions and still visit all the vertices. Yeah. That's a good question. So the question was, why do you need the middle vertex as opposed to just having 2, B out and B in? I think what can happen, so I believe what can happen is that you can end up doing something where you go A out, B in, and then you go off. You go off to another out. So the purpose of having that intermediate vertex is that when I go into B in to visit B, I've got to immediately go to B and then to B out. Like it ensures that after I visit B in, I have to visit B out in any tour. If there wasn't an intermediate vertex, then maybe my tour could somehow visit B in, go off to somewhere else, and then come back and then hit B out on a different part of the tour. So it's like, right, because there's no incoming or outgoing edges to B other than from B in and from B out. So but it's a great question. But it's kind of the same flow control idea, right? So anyway, I'm not actually going to do the reduction in any more detail. I just wanted to show you, that like we reduced to directed Hamiltonian cycle, but you can then reduce from directed Hamiltonian cycle to just regular Hamiltonian cycle using this trick. And now we've given a reduction from SAT to Hamiltonian cycle. Right, showing that. And what that says in our language would be that Hamiltonian cycle is at least as hard as SAT. Right? Because a Hamiltonian cycle solver could now solve a SAT problem if you discovered one. So the last reduction is the big one. And it is trying to argue that any problem in NP can be reduced to something. It's establishing that a problem actually is NP complete, that there is a problem in that set. Once I show there's a problem in that set, then to show that there's another problem in that set, I would just have to give a reduction from that one problem I know is an NP complete to this new problem. So for example, right, what we're actually going to show is that SAT is NP complete directly. We're going to show that any problem in NP reduces to SAT. Now, since we just constructed a reduction from SAT to Hamiltonian cycle, we then will have also shown that Hamiltonian cycle is NP complete. Right? And since like I drew that figure that had all these different connections, it starts to show that like everything's in NP complete, or not everything, but all these hard problems are in NP complete. And so I was mentioning this to someone after class, but this is exactly, there's a paper, a famous paper by someone named Richard Karp that was like the first paper to kind of establish this idea or like establish certain problems were in NP complete, this class. And they're called Karp's 21 problems. And he just goes through in one paper and proves that 21 different problems are in NP complete. It includes SAT, Hamiltonian cycle, subset sum, vertex cover, set cover, partition, a bunch of other ones that you may or may not have heard of, knapsack, just goes through one by one and reduces them all to one another, basically. First establishes one is an NP complete and then starts giving reductions from that problem to other problems. So now we're going to try and prove any problem in NP can be reduced to SAT. And I'll fully admit this argument is not 100% watertight as I'm presenting it. It's a little bit hand wavy in one spot. And that's just because like to do it totally rigorously would take us a lot of time and be kind of beyond the scope of this course. So, but I think it gives you the indication, hopefully enough to believe why this is true. And what we're actually going to do is any problem in NP can be reduced to circuit SAT, which I haven't told you about yet. And then circuit SAT can be reduced to SAT. So we're going to do it in 2 steps. So let's begin with circuit SAT. So a Boolean circuit is a directed acyclic graph. It's a DAG. And its vertices are gates. And the gates can be and or not. So and has 2 incoming edges that you perform an and on, or also has 2 incoming edges. Not has 1. And then there's inputs. There's known inputs, which would just be true or false. They're just things that are assigned. And there's unknown inputs, which we'll write with a question mark in them. And they can be assigned by us to be either true or false. And there's an output, which you call it's a sink. It has no incoming edge or no outgoing edges from it of the DAG. And it's our output, and we want the output to be true. So basically, the circuit sat problem is, can I make an assignment to the unknown inputs of true, false, such that the output of this circuit is true? So we've got all those gates, and you have the output gate. And our unknown input is going to be like vertices with question marks in them. So an example of such a graph is this. Let's say we have two unknown inputs and a known input, which is true. The two unknown inputs go into an OR gate. These two go into an AND gate. The result of those goes into an OR. I'm running out of space that way, so I'm going to go off on an angle here. That goes into a NOT gate, and that gives us our output node. And so then the question is, can I assign true, false to the two question mark nodes so that the output evaluates to true? Maybe you can look at it for a second and see if you can figure out an assignment. I think it kind of helps to just work backward from the output, right? Yeah. False, false. I think that's right. So since we've got an assignment, I'll go from the top, right? So two falses come into the OR. So the output is false. A false and a true go into the AND. So the output of that one is also false. So now I've got false and false going into this OR. Out of that comes another false. Then I take NOT, that becomes true, and then the output is true. So that is so false, false is a satisfying assignment. Okay. So then, like I said, that's circuit sat. Given a Boolean circuit, find a truth assignment for the unknown inputs such that the output equals true, or determine that no such assignment exists. This is a well-defined search problem. You can confirm it satisfies our two properties to be well-defined, right? Recall that those are, one, the solution has to be polynomial size in the input. That's clearly true here. We're just assigning true or false to a subset of the nodes in the graph. And the other is that I have to be able to verify in polynomial time that a candidate solution is a solution. And we kind of did that, I mean, by inspection through, when we looked at the assignment that was proposed there, right? The false, false. You just follow all the outgoing edges. At each gate, you compute the result, right? That's like a constant time operation. It takes in at most two edges and provides an output, and keep marching down your directed acyclic graph. So you could definitely do this in polynomial time. The other thing is that it's a generalization of SAT. Like, you can very easily express a SAT instance in this form. And let me just convince you that you can express a SAT instance as a circuit SAT problem. The one that's actually going to be more interesting is going the other way. If I'm given a circuit SAT instance, how do I write it as just a regular SAT instance? And in particular, a SAT instance in that CNF form that we've been talking about, where you've got just ORs in your clauses, and your clauses are connected by ANDs. But first, let's do this one. And I'll just do this by example, just to kind of convince you that it would be easy to write to go this way. So let's say I have a SAT formula that looks like, x1 or x2 or x3 and not x3 or x4. So in my circuit, I just create an unknown input for each variable. And then I'm just going to have them flow into some ors to make up the clauses. And then I'm going to have them flow into some ands to do the ands between clauses. Right? I mean, the only thing that I think this would be like trivial if I allowed or to take in more than 2. You know, like the only thing is that I said or only takes in 2 signals. So you have to like chain them together if you want to do an or of say 4 variables. You have to take in an or of 2 and an or of another 2, and then the outputs of those go into another or, right? And then that gives you an or of all 4 of them. But otherwise, it's pretty easy. It's just going to be some ors followed by some ands and then the output. So I'll draw it for this one. We would go circuit is x1, x2, x3, x4. I have to make x1 or x2 or x3. So I'm going to need 2 ors to do that. I go into an or, let's say with these 2, and then the output of that goes into another or. And the other one is not x3 or x4. So there's, I forgot to say, there'll be some nots as well, right? Take a not. That then gives me my second clause. So the left branch there, like this stuff, right, just created that clause. And this stuff here created that clause. And then I do an and to capture this, and that'll be my output. So it's just going to be, I mean, writing this kind of informally, a bunch of nots and ors followed by ands. And that's why I say it's a special case, just because it takes this special format that it's always going to be the ors and nots, and then the ands, and then there's not any more ors after that. You know, it's like separated in this nice way. Whereas a general circuit SAT instance could be all mixed up, like with ors and ands and more ors and stuff. Okay. And then on the other hand, and this is the slightly more challenging one, is let's say I'm given a circuit SAT instance. How do I write it as SAT in that conjunctive normal form? It's not too bad, but it is a little bit, like it just requires a little bit of playing with clauses to make them appear in the form of a CNF clause with just nots, like literals with ors in between. Any questions on this before I continue to this next step? So just to map out what we're doing, I'm going to reduce take an arbitrary problem in NP. I'm going to reduce it to circuit SAT, and then I'm going to reduce circuit SAT to SAT. So right now I'm doing the second piece. I'm reducing circuit SAT to SAT, and then I'm finally going to go back and take an arbitrary problem in NP and somehow try to reduce it to circuit SAT. And that's where there's going to be a slight bit of hand waving going on. Okay, so let's do circuit sat to sat. The idea is going to be that I have to like encode the logic of a gate, right? Like an OR gate has a certain logic, so that if the clause is set to true, the logic of the gate is obeyed. Like the inputs and outputs have to satisfy the logic of that gate. So we represent the output of each gate with a variable, gi, and then create a sat formula such that the gate logic between inputs and outputs is captured when the formula is true. So let's go through the different pieces. Let's say we have a true gate. This is pretty straightforward. If you just have true, its output is some variable gi. Then the form of my clause is just going to be gi. Right, for the logic of that gate to make sense, for this, the output of my true gate has to be true, right? And so for that to make sense, my clause that just has gi in it has to be set to true. I mean, it sounds like this one's easy, so it sounds like I'm saying nothing, just like, but I think it helps to think about this one to get to the more complicated ones. Okay, false gate is no more complicated though. So if instead I have false as an output, my variable is gi. The gi should be false coming out of that gate. So my form in sat is just going to be not gi. Maybe I'll write sat formula. Okay, let's do an OR gate because it's a little bit more interesting. So an OR gate takes in two inputs, H1, H2. They go into my OR, and out comes my output, gi. And the logic of that gate, maybe it's useful to write it as a truth table so that you can see just, what are the logical assignments of the, so in the truth table, right, we would write H1, H2, and then the output gi. So this is a truth table. And you have the four possibilities for the inputs. Oops, it's a terrible line. So false, false, true, true, false, true, false, true, right? That's all four combos. So if both inputs are false, then the output is false. And if one of them is true, one of the inputs is true, then it's an OR gate, so the output is true. So now I want to write some clauses that encode that when those clauses are true, this relation is satisfied, right? So like the assignments, the satisfying truth assignments of the variables will be the ones that encode the same relations of true and false between the variables. So for example, if I got something that said true, false, false, then the clauses I create will have to evaluate to false, like one of them, right? So that doesn't obey the gate logic. So, okay. So if we think about what are the implications that we need to express? Well, how would I do this instead? What if I just tell you what the formula is? And then you see if you agree. because it's actually a little bit complicated. It has part of why it's complicated is just that I'm trying to write it in this CNF form. And so it's got 3 pieces to it. The first is that GI or not H2 and GI or not H1 and not GI or H1 or H2. Let me tell you what the 3 things encode, okay? Just so that so you can think of this as like an implication that says, take the negation of the second thing that appears. I mean, this is one way to think of it. So the H2 implies GI. So that first one is saying H2, if H2 is true, then GI should be true. The next one saying if H1 is true, then GI should be true. And the last one is saying if H1 is false and H2 is false, then GI should be false. Like, do you agree? So if I take the first clause, right? If H2 is true, then not H2 is false. And so to satisfy the clause, I have to set GI to true. So you agree it enforces that, like, if H2 is true, then GI has to be true, the first clause. The second clause, same logic. It encodes that if H1 is true, then GI has to be true. And the last clause you can see is it's just making sure like that it also does the right thing when both the inputs are false, right? So it says, if you look, if both H1 and H2 have been set to false, then the only way to satisfy that clause is to have not GI be true or GI to be false. So that's the 3 clauses, right? The first 2 get the true part right, and the last one gets the false part right. Yeah. Because it's going to end up going, in general, it'll go into another clause, like into another gate. Yeah. So this is this logic that we're writing is kind of linking all the variables, right? If you think about what we're doing, let me just go back up to this picture here. We're like, every edge becomes a variable, right? And then we're using the clauses to make sure that the edge assignments are consistent with one another, right? Like, if these 2 are false, then what has to come out is false as well. So the variable that happens here is false. And then we're going to get a variable down here as well, right? Which is the output. And so if you find a satisfying truth assignment to the SAT clause, then all the logic of the gates has been satisfied and the output is true. And if you can't find one, then there was no way to satisfy the logic of the gates, like to be consistent with the logic of the gates and make the output true. That's going to be what happens. Yeah. Yeah, I think that's right. Yeah. And I will say, right, the only reason this is painful to write out is because I'm trying to do it in this CNF form, because that's the way we've considered SAT, right? And I've been telling you that like that CNF form is not losing any generality. We can only consider SAT formulas in that form. But that then means that I should be able to take this arbitrary circuit SAT formula and write it in CNF SAT. So that's the only reason we're kind of going through this painful idea. Okay, so let's do the AND gate, and then we have the NOT gate, which is not so bad. So AND, I think once you see how OR works, then AND actually isn't bad either. Takes in 2 inputs. They go into my AND, and then out comes my output, which we'll call GI again. So think about have to get both outputs right, the true output and the false output. So the one thing I want to express is that if H1 is true and H2 is true, then GI is true. My clause for that is going to be not H1 or not H2 or GI. Right? You can see if H1 and H2 are both true, those first two literals are false, and so I have to set GI to true to satisfy the clause, right? To make the clause evaluate to true. And then the other ones are going to be, if one of the inputs is false, then the output has to be false, right? So that's going to be, and if H1, which way do I go? So if H1 is or not GI, right? So if H1 is false, then GI has to be false as well. And same with H2. This one is H1 equals false, implies GI equals false, and this one is H2. Okay. Last one is a NOT gate. So what I'm going to say, just like, because I don't want like this presentation to be making you nervous or like worried. Like, I'm not going to ask you to do this kind of construction on a final exam. That's not the idea. I want you to understand. Like, I want you to be kind of convinced, even if it's like a little bit hard to follow, to be convinced that this is true, that I can reduce circuit sat to sat, right? Because I want you in the end to be convinced that any problem in NP can be reduced to sat, thereby showing that there is actually a problem in this class NP-complete. Like, that's the important thing we're trying to get out of this. The construction is definitely a little bit hard to follow, although I think you should be able to like try and encode some things in SAT, right? And I think even in the 6th assignment, it asks you to do, to make a reduction from something to SAT. So anyway, let's do the last one, which is NOT gate. So it just takes in one input, H, you have the NOT, and then out comes the output, GI. And the formula has to encode both things, the true and the false, right? So the true side is if H is true, then GI has to be false. Right, the only way to satisfy that is to make them opposites, essentially. Or the other option is that if H is true, then GI, GI. One of them has to be true and one of them has to be false, is essentially what that's saying. So this is H is false, implies G is true. And this one is H is true, implies oops. implies G is false. Is that true? Yeah, sorry. Yeah, exactly. I'm like looking at it and thinking I've written something funky. The first one, yeah, exactly. Sorry. I was like, that's why I'm pausing. I'm like reading what I'm writing and it's not making sense. First one says, if H is true, then G should be false. Right, we can see that in there. If I set H to true, then not H is false. And so then I have to set GI, not GI to true, which means I set GI to false. And the other one is the opposite, yeah. That if I set H to false, then I have to set G to true in order to satisfy the second clause. Yeah, thanks, sorry about that. Okay, so then what do? Then we replace each circuit, each gate in the circuit with the appropriate SAT clause. You also have, the true, like you have the unknown ones at the top, right? Which are just going to be, or you have the XI's coming in at the top, which are the unknown inputs. Or sorry, the question marks coming in for the unknown inputs, and then you have the known inputs, which are true and false. And a satisfying truth assignment of the SAT formula gives a truth assignment for the unknown inputs in the circuit SAT instance, along with the value of the output of each gate, right? Because we actually have variables for every gate output. And if it can't find a satisfying truth assignment, that means that there's no way for the output to be true while satisfying the logic of all the gates. And you can argue that this reduction is polynomial time. And so with this, we've now encoded any circuit SAT formula in SAT. We've given a reduction from circuit SAT to SAT. So that's the piece. And then the last thing is going to be, how do we reduce any problem in NP to circuit SAT? So let's take a 5-minute break and then we'll try that. So what we're now going to try and do is reduce any problem in NP to circuit SAT. And the thing that's, to me, challenging about trying to do this is, what problem are we talking about? Let's just take a problem in NP. Call it problem A. What do I know about it? Like, how do I do this reduction when I don't even know what the problem is? You know, it's not like I'm telling you it's Dijkstra or it's a shortest path or something like that, right? So all we know about the problem is that it's in NP, so it's a well-defined search problem. That's all we can leverage, right? So A is a search problem and it's well-defined. The fact that it's well-defined means that there is an algorithm that runs in polynomial time that can check if S is a solution to instance I. Right? That's by definition of well-defined search problem, is there's a way to verify that a solution is indeed a solution. So, and that algorithm runs in polynomial time, right? That was what was required for it to be a well-defined search problem. So what does that look like? Well, that algorithm takes in two things. Takes in an instance I, it takes in a solution S. They go into my algorithm C, and out comes true or false, right? It tells you, yes, that's a solution to I, or no, it's not. So this is the problem instance. So for example, in Hamiltonian cycle, that's the graph. And S is the solution, right? So it would be a sequence of vertices. And now you need to check, does that sequence of vertices actually constitute a Hamiltonian cycle in that graph? Okay. And now this is where things get a little bit imprecise, but the spirit, I hope you can agree with, is the algorithm C is polynomial time. It runs on a computer. right? What is a computer at its heart? It is just a Boolean circuit. Like it's a combinational circuit. It runs in time, right? I mean, at an incredibly high frequency. But if you think at like each instance in time, you just have a circuit, which is a bunch of ands and ors and not gates. And the output of that like cycle t is the input to cycle t plus 1 of the CPU. Okay. I mean, I know it's getting abstract because like that circuit is enormous. Like there's 100 million or a billion or something transistors in a modern chip, right? So this is big, but it does run in polynomial time, right? The number of copies of that circuit, I take the one from the first cycle of the CPU, and the output values of that gate go as input to the copy of that whole circuit at time step 2, which go time step 3, right? This is number of time steps is enormous, but it is polynomial. That's what it means, right? It's just the constant is enormous because we're running at very high frequencies, right? So anyway, this is my argument, is that any polynomial time algorithm can be written as a circuit. The algorithm runs on a computer, and the computer is ultimately a Boolean combinational circuit implemented on a chip. And so in theory, any polynomial time algorithm can be rendered as a Boolean circuit. There's polynomially many copies of the computer's circuit, one per unit of time. And the gate values for the copy at time t are used to compute the values of the gates for the copy at time t plus 1. This is a little hand wavy, right? But you kind of get the essence, right? This is enormous, but it is actually polynomial. It's like, it runs 5 billion times. The circuit is a billion gates. Okay, that's still actually, like it's scaling, the constants are enormous, but it is scaling polynomially with the input. So this is now the argument that we're going to use. And so we can write C as a Boolean circuit, and then we create a circuit SAT instance for the problem. And so the instance looks very much like our picture above. We have I, we have S, this goes into our circuit for algorithm C. And that is our output, which is true or false, right? Is S a solution to problem instance I? And now, how do we make this actually solve things instead of, right now, we're just saying this is like a circuit representation of our algorithm C? Well, in the other version, we're given I as an input. S is unknown. So S is our unknown inputs. I are our known inputs. And this is just an instance of circuit SAT. Right? These are our known inputs. We don't know the solution. It's the thing we're trying to find. Those are our unknown inputs. And if you could solve that circuit SAT instance, it would give you an assignment of true false to all the unknown inputs such that the output is true. In other words, it would find a solution S to the instance I. So solving this circuit SAT problem either gives us a satisfying truth assignment to the unknown inputs, meaning it would be a solution for which our algorithm C determines that yes, S is a solution to I. So I mean, it is a true solution. Or it tells you that no solution exists. Right? It can't find an assignment to the variables in S in order to make the output of the algorithm, the checking algorithm, true. So it can't find a solution to instance I, in which case no solution exists. So you either get a solution S or you get no solution S exists. And if you agree with that argument, then we've now shown that any problem in NP reduces to SAT. Now, how could I make this argument? Let's finish this, and then I'll just talk to you about this a little bit. So the reduction is complete. We've now shown that any problem in NP can be reduced to circuit SAT, which can be reduced to SAT. This then shows that circuit SAT is NP complete. It also shows that CNF SAT in CNF form is NP complete. Pair it with what we talked about at the beginning or the end of last class, in the beginning of this one, it then shows that directed Hamiltonian cycle is NP complete, which then shows that undirected Hamiltonian cycle by that 3 vertex thing that I showed you, that actually is NP complete as well, which then shows, right? I mean, it keeps cascading. So, of course, the hand wavy bit is this idea that I'm talking to you about a computer chip and implementing it as a Boolean circuit. If I wanted to do this a bit more precisely, we should have a model of computation. Like rather than talking about integrated circuits, we talk about a more like basic model of computation. And this is what a Turing machine is. It's very simple because it dates back, but it's basically a tape, like a physical tape with a head that can write into positions on the tape. I mean, it's not a real object. It's like something to think about. And you can show that any algorithm can be implemented on a Turing machine. And then we can talk about things everything in terms of Turing machines. So how do I take an algorithm that's implemented on a Turing machine and convert it to a circuit SAT instance? And this can be done precisely, this whole idea. But to do this, we just have to go into all that stuff, which, yeah. So you're asking about polynomially many copies of the computer circuit. So the algorithm runs in polynomial time, right, in the input size. So like that means that the actual execution time of the algorithm is bounded by some polynomial in the input. And then we know that the computer chip, just the number of cycles is just a constant times the time it runs. I mean, that constant is enormous, right? It depends on the frequency of your CPU, but that's the argument, right? In big O notation, that's just some constant. And then the input is only scaling, it tells you that it runs in 10 seconds. Okay, that's 10 seconds times the frequency of your processor. Yeah. So that's why I'm saying it's not that precise, but for the purposes of this course where we're not theoretical computer scientists, right? At this moment, most of us, and we're not going to go into the theory of computation and Turing machines and all of the sort of the details that you would need to fully 100% rigorously make this argument. Yeah. The most confusing for me, so you have to define, like the known inputs would be like the graph or something like that, right? Like let's think of the case of that this is Hamiltonian cycle or something. So you have to be able to represent the graph as Boolean variables, trues and true false in some form. Yes. I mean, this is just an instance, right? So it would just be like, you just need to have a convention, right? Like let's say you let variables, you introduce, I don't know, xij is true if there's an edge from vertex I to vertex j. And xij, this for the instance I, is false if there's no edge from vertex I to vertex j. And then you have all these things which are like your edge variables that get input into this circuit instance. The instance is just the input, like really is. It's the, like in Dijkstra's algorithm, it's the graph plus the start vertex, you know, or in shortest path, right? In sorting, it's the array, right? So it's always just the actual instance, and then like the, you know, the sort of problem in some sense is encoded in this algorithm that can verify a solution to an instance. Yeah. I fully agree with you. Like this is, I think it's like a kind of nice argument. It gives you some idea. It's not 100% satisfying, right? Like you're kind of left feeling, okay, I kind of get it, but it's a little bit hazy, right? That's because it is. The argument isn't totally precise. We don't have all the tools in this course to give it 100% precisely. Yeah. So, yeah, exactly. You're just given, exactly. You're given a search problem A. So now you know what its instances look like. So in theory, then you could make this thing that takes in an instance in Boolean format, right? Like as binary variables. That's what ends up happening in a computer anyway, right? For certain definition of variables, you represent the input in binary. But yeah, it's complicated to think of actually doing this in practice, right? This is a theoretical argument. But with this, we've now shown, maybe the thing that now I want to just summarize is this idea that we've gone over in this chapter, right? So we've talked about the notion of search problems, right? Well-defined search problems. They have an output of yes or no. And if they're well-defined, then if you claim the answer is yes, you can give me the solution and I can verify that it is a solution, right? So in SAT, I can plug in the variables and check that every clause has evaluates to true. NP is the class of all these well-defined search problems. P is the class of all problems that can be solved in polynomial time. And NP-complete is the set of all problems in NP such that any other problem in NP can be reduced to it. And so if you knew a problem is in NP-complete, then adding another one is just reducing that new problem, or reducing your known problem to this new problem. The challenge is in establishing something is actually in NP-complete. And that's the argument we've just been trying to go through, to argue that circuit SAT is actually in NP-complete from first principles, right? Take this unknown problem in NP and reduce it. Now that we have that something's in there, we can pull other things into it as well. And that's what we've done through a few different reductions with Hamiltonian cycle and SAT or TSP and all these things. So the things that you should be able to do, like coming out of this section, is answer a question if I say, is this problem NP-complete? Or show that this problem is NP-complete. Things you want to show is, one, it's in NP, right? It's a well-defined search problem. And two, give a reduction from like a known NP-complete problem to this new problem. The other thing you should be able to do is construct a reduction between two problems in NP, right? Or if I say one's NP-complete and I give you another one and ask you to do a reduction. And that will definitely be like one of the questions on the final exam will be, it'll give you a couple problems, like very much like this latest assignment, and ask you to do reductions between them, you know? ask you if it's in NP, this kind of stuff. Yeah.
Is there a way to figure out which problem?
No. So the question was, yeah, is it possible to figure out which problem is easily converted to another? And no, and in fact, it's something that even in like my research comes up, that like you often have a tendency to say, okay, these two problems look really similar, so it should be simple to reduce from this one to this one. That can actually lead you astray. Sometimes the best problem to go from is like just the most general one. So like it can be easier to go from SAT to something, even though it doesn't look like the problem you're trying to reduce it to. It could be easier to do that than to go from like another graph problem that looks a lot like it. So it's kind of misleading. Like you sort of have to try it out. I mean, for our course, often I'll give you the two problems, or I'll say like use an existing problem from class like that we covered in class, and there's only like 5 or 6 of them. So your bank is pretty small, right? Like, but yeah, it's a good question. Okay, so I think that's all I wanted to cover for today. Next week, we'll go into the final chapter, which is the coping with NP-Completeness. And I think we should finish just next week, and then we probably can just come and meet in the last lecture for a review or something if we want to do anything. All right, thanks everyone.